A force homework packet. Let's take a look at the reading preview, key concepts and key terms. How is a force described? How are unbalanced and balanced forces related to an object's motion? Key terms are force, Newton, net force, unbalanced forces, and balanced forces. Let's start. A hard kick sends a soccer ball shooting down the field toward the goal. Just in time, the goalie leaps forward, stops the ball, and quickly kicks it in the opposite direction. In a soccer game, the ball is rarely still. Its motion is constantly changing. Why? What causes an object to start moving, stop moving, or change direction? The answer is force. What is a force? In science, the word force has a simple and specific meaning. A force is a push or a pull. When one object pushes or pulls another object, you say that the first object exerts a force on the second object. You exert a force on a computer key when you push it, and on a chair when you pull it away from a table. Like velocity and acceleration, a force is described by its strength and the direction in which it acts. If you push on a door, you exert a force in a different direction than if you pull on the door. The strength of a force is measured in the SI unit called the Newton. This unit is named after the English scientist and mathematician Isaac Newton. You exert about 1 Newton of force when you lift a small lemon. The direction and strength of a force can be represented by an arrow. The arrow points in the direction of a force. The length of the arrow tells you the strength of the force. The longer the arrow, the greater the force. Combining forces. Often, more than a single force acts on an object at one time. The combination of all forces acting on an object is called the net force. The net force determines whether an object moves and also in which direction it moves. When forces act in the same direction, the net force can be found by adding the strengths of the individual forces. In Figure 2, the lengths of the two arrows, which represent two forces, are added together to find the net force. For example here, these two arrows are going in the same direction, so you would add them together and you would get a net force of 10 newtons towards the right. When forces act in opposite directions, they also combine to produce a net force. However, you must pay attention to the direction of each force. Adding a force acting in one direction to a force acting in the opposite direction is the same as adding a positive number to a negative number. So, when two forces act in opposite directions, they combine by subtraction. The net force always acts in the direction of the greater force. If the opposing forces are of equal strength, there is no net force. There is no change in the object's motion. Here you have 5 newtons going to the right, 10 newtons to the left. They're working against each other. So then you would subtract 5 from 10 and you would get a net force of 5 newtons to the left. Here you have 5 newtons to the right, 5 newtons to the left. They cancel each other out, and so your net force is 0 newtons. No net force. Taking a look at this diagram, you have these two students pushing a bookcase together. Both are pushing to the right. Here are their individual forces, and their net force would result in a movement of the bookcase to the right. If they are each pushing on a different side towards each other, you would have to take a look here. His individual force is bigger than her individual force, so the net force is going to result in movement to the right. Unbalanced forces. Whenever there is a net force acting on an object, the forces are unbalanced. Unbalanced forces can cause an object to start moving, stop moving, or change direction. Unbalanced forces acting on an object result in a net force and cause a change in the object's motion. So unbalanced forces result in some kind of net force which is going to change the object's motion. Figure 3 shows two people exerting forces on a box. When they both push a box to the right, their individual forces add together to produce a net force in that direction. Since a net, or unbalanced force, acts on the box moves to the right. When the two people push the box in opposite directions, the net force on the box is the difference between their individual forces. Because the boy pushes with a greater force than the girl, their forces are unbalanced and a net force acts on the box to the right. As a result, the box moves to the right. Balanced forces. When forces are exerted on an object, the object's motion does not always change. In an arm wrestling contest, each person exerts a force on the other's arm, but the two forces are exerted in opposite directions. Even though both people push hard, their arm positions may not change. Equal forces acting on one object in opposite directions are called balanced forces. Each force is balanced by the other. So, for example, these two girls push the bookcase or box, whatever we want to say, towards each other with the same amount of force. Nothing is going to happen. That bookcase is not going to move. Balanced forces acting on an object do not change the object's motion. When equal forces are exerted in opposite directions, there is no net force. In figure 3, when two people push on the box with equal force in opposite directions, the forces balance each other and the box does not move, which is what I just said. Sorry for being repetitive. Let's read about spring scales. The SI unit of force. There are different SI units for different types of measurements. For example, the basic unit of distance is the meter. The basic unit of mass is the kilogram. The newton is the basic SI unit of force. The unit is named in honor of Sir Isaac Newton. On Earth, it takes a force equal to 9.8 newtons to lift a 1 kilogram mass. Weight is a familiar example of force. An object's weight is a measure of the force of gravity acting on the object. When you weigh an object, you measure the pull of gravity on the object. Because weight is a force, an object's weight is measured in newtons. For example, an object that weighs 15 newtons is heavier than an object that weighs 10 newtons when weighed at the same location. Using a spring scale. A spring scale is used to measure weight. A spring scale measures the force of gravity on an object. Figure 1212, this, shows the main parts of a spring scale. So you've got a spring, you've got a pointer, you've got the scale on the outside. The pointer is the doohickey on the outside that matches up with the numbers here on the scale. And here you've got a weight on it, and you see where it's pulling the spring down to. To use the scale, attach a mass to the hook. The weight of the mass stretches the spring. The pointer moves down along the scale. The number at which the pointer stops is the object's weight. For example, suppose one mass moves the pointer to 5 and another mass moves the pointer to 1. The first mass weighs 5 times as much as the other mass. What does a spring scale measure? Force, and weight is an example of a force. Types of spring scales. There are many types of spring scales. The scale shown in figure 1212 is similar to the type of spring scale used in a science lab. Many bathroom scales are also spring scales. When you stand on the scale, your weight pushes on a spring. The spring causes a circular scale to turn until the number on the scale lines up with the pointer. This number shows your weight. Another type of spring scale is the one you see in the fruit and vegetable section of a market. If you place some grapes or apples in the scale, the weight of the fruit pulls a spring. The spring turns the pointer to show the weight of the fruit. I was actually just commenting today that my grocery store doesn't have these, and it's frustrating because you want to know how much food by the pound is going to cost you. But that's not your problem, that's mine. All right, speed skating. A high-powered machine lets racers rest their legs while they soar on skates. Cool. Oh boy, quite the name here. Engineer Jorg Collert, I probably messed that up, zips into a padded leather bodysuit. He straps on a helmet and goggles, dons elbow and knee pads, and pulls gloves onto his hands. Seconds later, the need for serious safety equipment is clear. Rolling on only the small wheels of his inline skates, Collert races around a track at more than 90 kilometers an hour, which is 56 miles an hour. Collert doesn't rely on Superman-like legs to reach such breathtaking speeds on skates. Rather, he hitches a ride behind the latest in extreme sports equipment, the Scooter-Skate. This wheeled machine, resembling a cross between a lawnmower and a motorcycle, has a high-powered engine. Collert and colleagues created the machine to tow trained and daring skaters to speeds much faster than they could reach themselves. Muscle Normally, to reach top speeds on skates, a person uses pure leg strength, pumping back and forth against the road. The skater exerts a big force on the ground, says Stephen Manley, a physicist at the University of Rochester in New York. And according to Newton's third law of motion, the ground pushes back with an equal and opposite force, propelling the skater forward. With each leg pump, the skater's speed increases, but using only these forces, even top inline skaters can't attain speeds reached with the scooter skate. That's because each backward stroke of the leg requires a skater to perform work, or a force that moves an object through a distance. To do the work, the skater's body converts chemical energy gained from food into mechanical energy, which moves the skater's leg muscles. But the power, or the rate at which a person can convert that energy, is limited. Power is the rate at which energy is converted from one form to another, or transferred from one object to another. Consider a high-watt light bulb. Each second, it converts more electrical energy to light energy and heat energy than a bulb with a lower wattage. Power source. To surpass the speed limit set by leg power, the scooter skate propels skaters with engine power. The engine converts gasoline's chemical energy, which is energy stored in chemical compounds, into mechanical energy to rotate the machine's front wheel and tow the skater. One racing model of scooter skate boasts a mighty 2,700 watt unit of power engine. So it has a 2,700 watt engine. Even a top skater's power pales in comparison. A trained athlete can put out about 400 watts of mechanical power for fairly long periods of time, says Chris Waltham, a physicist at the University of British Columbia in Vancouver, Canada. Scooter stunts. Whew, that's hard to say. With the added power of a scooter skate engine, Collard and other skilled skaters in Europe are strapping on safety gear to race each other on enclosed tracks at mind-blowing speeds. Specially trained stunt skaters are also using scooter skates to enhance their routines. These skaters can rocket off jumps and perform mid-air flips and spins. The amount of time they can spend in the air depends in part on their speed when they leave the ramp, explains Manley. To fly sky high, these skaters... Why is this so difficult? Oh dear, I'm sorry. To fly sky high, these skaters need to build an extreme vertical velocity, or speed, in one direction. It helps them fight against the force of gravity, pulling them back toward Earth. With the extra speed supplied by a scooter skate, these trained daredevil skaters can rocket higher off the ramps and pull record-breaking stunts. That's it. Hopefully this helped you.